Welcome back to the concluding class of the summation of series. So this is Mittag-Lefflers Expansion theorem. So it's one of the methods that is being used in summing up series. Let f of z be a meromorphic function whose singularities is the finite part of the plane as simple pole. At these are the simple poles and these are the residues. The residues of this pole, they are this. Then Mittag-Lefflers expansion theorem says that f of z is equal to f of 0 plus this series. So this is called Mittag-Lefflers expansion theorem. We do use this series in summation of series. And let's take example. Example 1 here. Show that this is equal to this. Before we do this, we need to know our f of z solution. The best way to do is to say that your f of z is pi over sine pi z. You bring this one here, so it will be minus 1 over z. So you let your f of z to be that. And this, if you simplify further, will give us pi z minus sine pi z over z sine pi z. Now, this is the formula here. There's f of 0. That means we need f of 0. There are three things we need here. We need the singular point and we need the residue. At the singular point, we need the pole here and the residue. So I will need f of 0. So if you put z to be 0 here, you observe that it will make the whole of this to be 0 over 0, which is undefined. So what we do is that in order to find your f of 0, you write it like this. Your f of 0 is limit of z tends to 0 f of z. So this will be limit of z tends to 0. You put this value there, pi z minus sine pi z over z sine pi z. So this is, we are taking it to limit now. So we make use of L'Hospital rule. That is, we differentiate the numerator and the denominator separately. If I differentiate this, I will have pi. And if I differentiate this, I will have minus pi cos pi z. For the denominator, if I differentiate this, I will use product rule. So that will be sine pi z. So I've taken this, I'll differentiate this. Plus, I'll take this now, I'll differentiate this. That will be pi z cos pi z. So we cannot put our z to be 0. If you put your z to be 0, this will be pi minus pi, because cos 0 is 1. This one, if you put your z to be 0, this will be 0 plus 0 again. So you see that it is 0 over 0 again. So we still apply L'Hospital rule. Now let us apply L'Hospital rule again. That is, we differentiate this. If I differentiate this, I should have pi squared sine pi z. You know, if you differentiate cos, we get sine, minus sine. That will be over, I'll differentiate this. This will be pi cos pi z. And for this, I'll make use of product rule. If I differentiate this, I will have pi cos pi z plus, if I differentiate cos, I will have minus sign. So it will be minus. Pi will come out. It will become pi square z sine pi z. So putting z to be 0, this will be 0 on top, divided by this one will be pi here. This will be another pi, but this will be 0. So our answer there is 0. So therefore our f of 0 is 0. So let's keep that. Also, we need the singular point there. So let's write out our f of z again. Pi z minus sine pi z over z sine pi z. So this is the function once again. So we need to get the singular point. So merely looking at it, you see that z is equal to 0 and sine pi z equal to 0 will give us our singular point. But following what we get here, as limit of f of z tends to 0 simply means that 0 is a removable singularity, and hence it is not a pole, because it gives us something. It exists here when we found the limit as z tends to 0. So in that case, we remove this. This is not a singular point. So to get our singular point now, our singular point will occur at sine pi z is equal to 0, or if you make pi z the 0 formula, this will be arc sine 0, and arc sine 0 will give you n pi. For all n is equal to 0, plus or minus 1, plus or minus 2, and so on. From this place now, pi cancel pi. Therefore, z is equal to n. But here, we have said that z is equal to 0 is not a singular point. So in this case, we remove 0. We cannot say that n is equal to plus or minus 1, plus or minus 2, and so on and so forth. So we have known our singular point, which is z is equal to n. So I cannot find the residue. So this singular point is our an. Our an is n. We have known that. So our residue, which is bn. So this singular point here, they are all simple poles. So we have z tends to n. Our n is the singular point. If you remember residue, still residue, z minus z naught. Our z naught is n times f of z. This is our f of z there. Pi z minus sine pi z divided by z sine pi z. This is n. If you put z to be n, you are going to have 0 over 0. So what you do is you differentiate. You use L'Hospital, you differentiate this separately, and you differentiate this separately. And when we are dealing with residue, calculation of residue, I've explained this type of concept. So in this case now, if you look at it, you see that if you take this and differentiate this, later if you substitute this to be 0, it will nullify. So we don't need this again. So that means I've taken this, I'll differentiate this. Now I'll take this, I'll differentiate this. Our answer is pi z minus sine pi z over, we differentiate the denominator too. That is sine pi z plus this. We are using product rule. We take this, we differentiate this. We take this now, we differentiate this. That is pi z sine pi z. From this place, I can now put z to be n, and taking note that sine nz is equal to 0, y cos nz, that will be minus 1 raised to power n. So let's take note of these two. This one is 0, but for cos nz, I say nz cos n pi is minus 1 raised to power 0. So in this case, let us put z to be n. So this will be n pi over, this is 0 already. This is 0, this is, the differentiation is cos. Now we differentiate sine. So this is n pi. Remember, cos is minus 1 raised to power n. So this cancels this. Finally, we have minus 1 raised to power n as our answer. That is the residue. So we can now come back to this place. Therefore, our f of z we are our f of z is pi over sine pi z minus 1 over z. It will be equal to, we substitute everything we got there, is equal to 0. F of 0 has given us 0, so this will be n runs from infinity to infinity. Bn, we have known our bn to be minus 1 raised to power n into 1 over z minus an. So we know that our an is n. So this is n plus 1 over n. Now this can be written as n runs from 1 to infinity minus 1 raised to power n into 1 over z minus n plus 1 over n plus n runs from minus 1 to minus infinity. So 0 is not there, so we put this there. Minus 1 raised to power n is here. 1 over z minus n plus 1 over n. In order for this boundary to be the same thing, what we do is that here we replace n by minus n. So this will be equal to n runs from 1 to infinity minus 1 raised to power n into 1 over z minus n plus 1 over n. So if you have replaced it, this will be n will be 1 to infinity. So we have said this is equal to minus n into 1 over, this will become z plus n. We have said n is minus n, so it will become minus z. Don't forget that this and this, they are just the same thing. So in that case, I can write it as this raised to infinity minus 1 raised to power n. I can merge them together so that they will become z minus this plus 1 over n. This is there again, plus 1 over z plus n minus 1 over n. This and this are gone. What we have left will be n runs from 1 to infinity minus 1 raised to power n. So we find the LCM. The LCM is z square minus n square. That is multiplication of these two. When we find the LCM and simplify, we have z plus n plus z minus n. From that place, we observe that minus n is gone. So what we have will be minus 1 raised to power n 2z, z plus z over z square minus n square. So that is our answer. We have example 2 here. We want to show that this is equal to this. As usual, our f of z is equal to 1 over this minus 1 over this. What did I do? I've picked this. I would just say minus 1 over z. I've brought this to the other side. That's our f of z. And if you rewrite it, it will become, so it will be this. When we want to find our f of 0, we substitute directly first. If you substitute directly, you will see that you have indeterminate form. So what you now do is you find the limit as z tends to 0, f of z. So you write the f of z. So that's how to find your f of 0 from the formula. Since we now have limit, now we use L'Hospital rule. That is, we differentiate this, we differentiate this. This is 1 minus exponential z. If you differentiate this, it will give you z exponential z plus exponential z minus 1. That is, when you differentiate, if you use product rule and you expand, you are going to get what is here. So substituting z to be 0, it will still give you intermediate form. So we still apply L'Hospital rule. So, and that will give me, if I apply L'Hospital rule again, this will be minus exponential z over, if you differentiate this, this is z exponential z plus exponential z. If I differentiate exponential z, I will have exponential z. Now, putting z to be 0, that will be minus exponential 0 over the whole of this will be 0 plus exponential 0 plus exponential 0. So this will give me minus half because exponential 0 is 1. Here we 1 plus 1, which is 2. So I have known my f of 0. My f of 0 is equal to minus half. Another thing I need to know is my singular point, the pole. And the singular point will occur at z into this is equal to 0. So that means z is equal to 0, exponential z minus 1 is equal to 0. Here, since the limit of z tends to 0 times f of z gives me a definite value, then z is equal to 0 is a removable singularity and it's not a pole. So we can only get our pole from this place. That is, exponential z is equal to 1. What can give me 1 in the theory of complex number is just 2 pi ni, any n at all. N runs from 0 to infinity, plus or minus. So this cancels this. Z will now be equal to 2 pi high n. Here now, n cannot start from 0 because if n starts from 0, that will be z is equal to 0, which we have said is not a pole. So n must start from minus 1, minus 2, up to plus or minus infinity, to be going like that. So I have known my pole. Therefore, our pole is which is an, and that is 2 pi ni. What do I need again? I need my bn, which is the residue. So the residue is limit of z tends to 2 pi ni. That will be z minus 2 pi ni times f of z. So these are f of z. We write it out. Now, if you substitute these values there, it will give you in definite form. So what we do is we apply El Hospital rule. And from what I have discussed the other time in our previous example, in this type of case, it is very easy. What we just do is that we write only this. We differentiate this. And that will be z exponential z plus exponential z minus 1. Now, exponential z minus 1 will always give me 0. So this will give me 0. So in this case, this will be, if you put there 2 pi ni, exponential z there will give me 1. This will be 1 as well. This is 2 pi ni. This is 1. Exponential z will give me 1 minus 1. So this will get lost. So finally our answer there will give me 1. These are what will remain. So they are the same thing, it will give me 1. So I have known my bn. I can now write my formula, the Mittag-Lefflers Expansion theorem formula. That will give me. Now we have written our f. We have known our f of z. From this place, let's write it out. Our f of z, and that will give me 1 over this minus 1 over this. Then f of 0. You observe our f of 0 is here. We got minus half. So in that case, this is minus half plus sum of n runs from minus infinity to infinity. Bn is 1, so we don't need it. So this will just be 1 over z minus z plus our an. That is a singular point. This is a singular point here. 2 pi ni plus 1 over 2 pi ni. So from that place, if you make this z formula, this will be minus half. When this one comes here, it becomes plus 1 over z plus, I can separate this to become n runs from 1 to infinity times what is inside plus n runs from minus 1 to minus infinity times what is inside as well. which is this. That is what is inside. Now let's continue from another page. This thing will now be equal to minus 1 plus 1 over z plus n runs from 1 to infinity times whatever. I don't want to rewrite it. This ought to be there. This is what I'm concerned about. Here we replace n by minus n. So it will turn that one to 1 to infinity. So this one will change to minus 2 pi ni. There's a mistake here. This is minus from the formula. This will be minus from the formula. So this will be it will make this place to be plus, because we are okay. This is minus as well for now. This is minus. Okay, so what is there is what is there, but this one will turn to plus, and this one will become minus 1 over 2 pi ni. Since they now have the same boundary in the summation, we can merge them together. So let's write what is inside this place. This is 1 over z minus 2 pi ni plus 1 over 2 pi ni, then plus this one 1 over z plus 2 pi ni, and minus 1 over 2 pi ni. So this and this are gone. So let's write out what we have left. So these are the two things that we are going to have left, and if you find the LCM, that should give me z minus 2 pi I n or ni and z plus 2 pi ni. So here will be z plus 2 pi ni plus z minus 2 pi ni. From that place, 2 pi ni is gone. So this will be this plus 1 over this plus n runs from 1 to infinity. What is on top will be 2 over z, and this will give me z squared minus 4 pi n squared, 4 pi squared n squared. How did we get that? 2 times 2 is 4. Pi times pi is pi square. So what we have left is ni. Minus times minus is minus. Let's keep it. Now n times n is n squared, minus I squared times I squared is I times I is I squared, so that is minus. So the double minus there, okay, it will make this place to be plus. So that simply means that what is there should be plus. So that completes the proof. That is what we are asked to prove. So you can practice the following. These are the questions. Practice the two. Practice the two. So the hint to this one, when you have shown this and you integrate both sides, so this result will come out. So have a nice day.